Well, thanks very much for inviting me here. I haven't been to Wales for nearly 15 years, so it's great to be in your wonderful environment. I belong to a company called Llewellyn Davis Yeang, and it's originally founded by His Lordship Lord Llewellyn Davies, and I joined them in 2005, and I've been living in London since. Most of my work over the last 2-3 decades have been on green design, which is what I wrote my doctorate on, and so I've never stopped doing anything else. The subject is such a big subject that I'm not going to cover most of my ideas today. I'll cover some of them, and I've tried to make it not theoretical and not too technical, but I'll try to make it as illustrative as I can. I have a certain series of ideas, which I call aphorisms, about green design, and so I'm going to go through a series of these as ideas that influence my work. The first has to do with handling biodiversity, and I believe that a lot of what we have to do has to start with looking at nature as a whole. And I believe that green design, it's not necessarily applicable to architecture or product design alone. It refers to everything that we do as human beings, in our activities and the things that we make, and how to integrate it with the natural environment. And so integrating everything that we make and do with the natural environment is extremely important, and I'm going to illustrate this in some of the ways that I've done it. One of the things that concern me is how to integrate vegetation, nature, with cities and with settlements. These are 3 diagrams that I did to try and illustrate the idea. It's a map of Manhattan, and so you could put, for instance, put all the vegetation in one location. As you can see in the first diagram, for centralized planting. Or you can disperse it in a series of spotty relationship. That's in the second diagram. Like in Georgia and London, if you like, you have a series of green squares, Bedford Square, Tavistock Square, Euston Square, and so forth. Or you can integrate it with a series of what I call the ecological corridor on fingers. From the ecologist's point of view, the last diagram is the preferred one, because the green areas are interconnected, and by being interconnected and linked, enable species to migrate from one part of the site to the other part of the site, enable species to interact. By being linked, it engenders a single larger habitat with greater volume of resources to be shared, and therefore it's much more stable. And so the last diagram, if you like, is the preferred pattern. So these are just patterns I use to inspire myself, what I do. Usually what I try and do is that I look at the building carcass, and one of the first things I do is to roof the garden to bring some vegetation on top of the building. Studies have shown, for instance, in Japan, that by roofing existing buildings, the gardens, by roofing top of existing buildings with gardens, species that they thought were lost have come back into the city, so that's a good thing to do. Then the next thing I try and do is to connect the vegetation with the ground plane, because then it becomes a much more integrated ecosystem. This is a master plan I did for Kowloon Waterfront, and it's right at the edge of the water of the MTR station, and you can see the red square shows where the vegetation mounts down to the ground. This is the perspective of the scheme, and at the back is the scheme done by MTR, and the big tall tower on the left-hand side is by a US architect firm. A lot of things we do is try and repair what has happened in nature, because green design is not just new buildings, not just doing things to existing buildings, but looking at the landscape and find out what the terrible things that we've done as human beings in the landscape, and how to repair it, how to reconnect it. Because most town planners fragment the land when they build. They divide the land with roads and drains, and they chop it up into little parcels. It's like turning a cow into a burger, just trim it like that. And so we look at the landscape and see how we can reconnect it. So with this scheme, what we tried to do was to connect with Kowloon Park by a bridge. And so in this way, the whole scheme extends to the bridge and to try and connect to adjoining sites as well. So in this way, we're able to give Hong Kong the single largest park we could have. And the next thing, after that, we tuck in the vegetation into the floors, as you can see here, to create some sort of sandwich. Now, if you look at any master plan or any city design, you see the buildings and the public spaces, and then that is glued together by the engineering infrastructure, which is the roads, the drains, the sewerage. My contention is that nature has its own infrastructure as well, and we should try and create this infrastructure as greenways in all our developments. In this way, we have both a parallel interface between the human-built environment and the natural environment. So with this scheme, the green infrastructure is really the roofscape and the bridges and the mounts that bring it back to the ground. So this is, if you like, nature's infrastructure, where nature has its own ways of moving between species, interacting, and invisible processes. So this led me to come to the conclusion that really green design is the integration of four basic infrastructures. The green infrastructure, which is nature's infrastructure. The grey infrastructure, which is the engineering infrastructure or the eco-technology infrastructure. The blue is the water infrastructure, which is the management of water that falls in the land, that should remain in the land rather than be drained into the sea or into water, into rivers, and it's gone forever. And then finally, the human infrastructure. You find that most master plans, or most designs, most eco-cities have the last three infrastructure. For instance, if you look at Dong Tang, designed by Arabs, it has a wonderful series of public spaces and systems for food production and so forth. It manages the water through bioswales and biofiltration pits and so forth. And it's very clever engineering technology that is low energy and seeks to be carbon free and so forth. But it hasn't got the green infrastructure. And so to me, when I look at a city design or a master plan, if it hasn't got any green infrastructure, it is not an eco-city, it's just a chunk of engineering or building. And so to me, these four armatures are extremely important: the green, the grey, and the blue and the red. I use the word red for human because that's the color of blood, not for any political reasons. So here's a scheme that we designed in India. And to illustrate this, here is the master plan. Sometimes you can't see the woods for the trees, so I'm just showing the land use plan, which is this. And so you can see the green bits that starts from the left-hand side. On the left-hand side of the page is a conservation area full of trees, and then we start with the green strip, and we stretch it across the side like stretching chewing gum. And so this becomes the determinant, if you like, of the master plan. And I contend that the green infrastructure should be the dominant infrastructure rather than the grey or the blue, any others, because that's the thing that we need to do to repair the landscape and to create a new landscape. So with this, you can see that this is the green infrastructure that is continuous, it is linked, it is brought right across the site. And in summary, the green is the green line. The blue are those filtration ponds, so that the water that falls in the land remains in the land. And that's grey, which is the roads and the drains and sewage and so forth. And then the yellow are the human settlements and open spaces. And that obviously includes the rules and regulations and laws that determine our society. Here's a close-up of the four infrastructure: the green, the blue and the dotted line, blue dotted line. The grey are the roads, the drains, and then there's the human, which is the yellow. Then I thought, well, if that's the case, if this is how we bring green design together, I believe I also believe that there are many ways to get to green design. I don't think this is the only one. When you speak to any of a dozen green architects throughout the world, they have different ways of doing this. But I seriously believe that we really got to have, I genuinely believe that we have to have these four infrastructures, otherwise it'd be nothing more than just engineering. You know, sometimes I pick up a magazine and I see an architecture done by a famous architect, and he says, I've done a green building. Then I look at it and I said, well, you know, it's just engineering. Yeah, all the photovoltaics, you have groundwater, heat source, and you know, solar collectors and water harvesting. But where is the green infrastructure? And so, yes, engineering has been very clever, and that these, you know, these buildings and these designs are useful experiments towards an eventual green architecture. But I don't think we have truly achieved green architecture 100%. But from the master plan idea of the green infrastructure, I thought, why don't we flip it vertically and have this green infrastructure in the building? And so this building, so this is the green infrastructure that starts from the ground, weaves its way up to the top of the building and the roof, and this happens at the back of the building as well. This is the plan of the ground floor of the building, and you can see the greenery that starts on the ground, and the dotted line shows where the ramps are, where it brings up the building into the top of the building. And the plan on the left-hand side is the first floor. The second is the second floor, and the third is the typical floor. I have a series of, so you can see the green strips that weaves its way up top of the building, and that's one in the back of the building, that's one in the front. And so that's the design for this building. There's another scheme for the waterfront in Macau, and this is the green infrastructure. This time we brought the green infrastructure into the hinterland with a bridge you can see on the left-hand side, and then vertically up to the top of the building. And so, back to something I said earlier on, green design is about repairing ecosystems, making devastated ecosystems whole. This is a competition scheme that we won in Istanbul, and our scheme is on the left-hand side. But the right-hand side shows what is green and what is human settlements. The red are the human settlements that have eaten into the countryside. You can imagine maybe 150 years ago, you know, the drawing on the right-hand side is all green. But we as human beings have just eat in the landscape, you know, and you can see probably if we're not careful in about 50 years' time, the whole of that drawing on the right-hand side would be all red. And so one of the things we wanted to do was to repair this, and you can see, you know the whole region covered with the human settlements. Now, this is not necessarily the fault of the town planners. You know, there are a lot of informal settlements and squatters, and they just build in the countryside, and then the political parties, you know, would come in and say, okay, we'll legalize the settlements and give you roads and drains, and so it becomes, you know, as a part of the city boundaries. So the idea was to relink the greenery, to try and link it together and try and make the ecosystem whole again. But how can we do this? Because you have existing highways, you have roads, you have existing buildings. And to relink it, the idea we had was what we call the landscape bridge. So now, for instance, you have two sides A and B, and it's separated by this road in between. But what happens if you bridge it and you vegetate it? So straight away what you've done is that you have improved the ecosystem interaction between the two plots, and you made them whole, you connected them. And this encourages, as you know, increase in species diversity, and again, as much as the ecosystem. So with this simple idea, we said, well, let's have a series of layers. We have the roads, then we have the eco bridges, and then we have the mass transit system over it. And so we want to reconnect from the northeast to the southeast, and the northwest to the southwest. And you can see here's the model, and the red squares show where the eco bridges are. So then in this way we have what was a previously ecosystem that's been chopped up and being broken up by human society and human development. It's now reconnected and made whole again. So you can see the three infrastructure. You can see the green, the red. I used the red color here to show the green, and then the blue colors, the blue water management system, and then the white is the highway or the grey infrastructure. To justify the commercial value of this, we started to map to find different activities that take place here to try and give Istanbul the single largest park you can have. And so here you are, we started to map more activities to make it commercially viable. Then we thought, well, if we just linking the vegetation to the ground and integrating the biotic components with the abiotic, can we do it vertically? And so the correlation of what you see, the first three diagrams, would be, at the bottom, you can either, again, put it on one location in a sky court in buildings, which a lot of architects are doing, actually. If you look at a lot of schemes done by big important architects in London today, and some of the major cities, they have sky courts with greenery. The second equivalent of dispersed planting is, I call it intermixing, and there's a spotty relationship. And obviously, the equivalent of the continuous planting is one that spirals all the way up to the top of the building. Now, biodiversity sort of sometimes depends on which part of the earth you're at. And UK's, well, where you are now, you're probably around 54 degrees above, 54 degrees latitude above the equator, a little bit higher than that red line there. And so you are not that biodiverse, but you are, you still have a lot of variety of species. In fact, when I was on the way here by car, the part of your countryside that has the highest biodiversity are your hedges. And so you try and keep your hedges as much as possible and stop farmers from cutting them down. One of the ways the idea we had was this scheme that we designed for Istanbul again, another scheme, where we thought maybe we have a series of ramps that sort of ramp from the ground up the side of the building. So the idea, this is the master plan for this site. It's almost surrounded by roads, but there is, fairly natural sort of ecological zone on the left-hand side. It's not sort of primary vegetation, it's probably secondary in a reasonably sort of advanced state of succession. And this time what we did was to have the vegetation that starts from the ground, ramp up to the side of the building, goes up to the wall, to the roof. And so you have to understand that what I'm trying to do at the same time is to trying to find out what an ecological aesthetic is. Because I believe the green building should look green and it should have its own aesthetic. The other day I was in Vancouver with a client, and my local architect was driving us around the city, and he pointed at the building which he said was certified LEED Platinum. Obviously, LEED Platinum is the highest rating you can get on the LEED certification system. My client looked at it and says, well, looks like any other building in the same street. And so, I think if you have a green building, it should look green, rather than give mixed messages to the public. So this is the green infrastructure that goes around the site. And so in Vancouver, we work on this series of towers, and the mayor's view is that he will give additional plot ratio, additional buildable area if you can show that the building to be green and super green. Because of the cold climate in Vancouver, it is no longer temperate climate, it's a cold climate. The greenery are inside an encased atrium that works its way up to the top of the building. So here we have the vegetation that starts from the ground, works its way up diagonally, and then at the bottom, it's sort of 1/3 of the way up, and 2/3 and 3/3 we would have green sky courts, and then on top of that over that we would have green bridges. So the linkage is not just at the ground plane, but also at the upper parts of the building. And we were able to achieve about 30% equivalent of the built-up space in greenery, both on the facades and in the sky courts. This is the plan of the project, and you can see this is the green infrastructure. So we try to link the greenery along the boulevard on top, and then over the retail and up the building and along the waterfront. Ecology sees the Earth as covered by this thin film, which is the biosphere, which is where living systems live, living organisms live. And then within the biosphere there are units which are called ecosystems, and ecosystems are defined by ecologists as consisting of both biological constituents and physical constituents, or biotic constituents and abiotic constituents acting together to form a whole. But what most architects, engineers, and designers is just building the physical environment. Most buildings that you find in cities are just inorganic, and probably the only thing organic about most of the buildings you see are just us as human beings and the bacteria and the bugs. And so with these patterns, we started to start in my early architectural life to try and integrate vegetation in buildings. This is one of the towers I did a few years back. I find this image emblematic for me. I find this image important because it represents the beginning for me what a green architecture should look like. It should be fuzzy, it should be indeterminate, and some of my friends call it hairy. Hairiest building in the world. So we had a series. So this is the floor plan of the building. It's here sky courts, and this is what it looks like from the outside. But they were not connected, So because this was an early project, I didn't really come to start trying to connect until much later on. But that's all right because there are certain species in nature like butterflies and insects and birds, actually go from one green patch to another green patch. But ideally, it should be connected, and so I did a drawing to show this connection. In some ways, this drawing and the other drawings represent the way I work. I would have an idea, and I would draw it up and try and use this as an icon for my other design. So this was a scheme that we designed in Singapore, which had vegetation going all the way up, and another scheme where we had planter boxes which are linked with trellises, and the boxes would have a gravity system that feeds water and fertilizer, so the whole building comes like a living organism. This is a very old building I did maybe 20 years ago, and here we can see the vegetation climbing up the sides, across the floor, to the top of the building. So vertical integration is extremely important for me, and what I showed earlier on was vertical integration upwards. So how do we integrate downwards? So one of the ideas we had was to have, I call them eco cells. They're like cells that cut into the building, goes all the way down to the basement. And so these are where the eco cells are in this project. And the eco cells do a number of things. They bring vegetation into the inner parts of the building, provide opportunities for rainwater harvesting, bring natural ventilation, bring daylight, and obviously it's sort of where the water retention pond could be, or could have a living machine for sewage. Here's an example of what these eco cells are, what eco cell could look like. This is the project we did in Singapore, which is in the National Library. This is the view from the ground plane. You can see the eco cell on the left-hand side, and at the lower floor where the library is, you can see people actually using the space. You can get daylight coming in. The building has been simulated in the design process, in the process of design, and this is. We put it through a wind tunnel test, and this is what it looks like inside the wind tunnel. Actually, we simulated the daylight and the energy efficiency. You can see that the building was completed in April. And this is a post-occupancy evaluation of the building. So, completed in April, you can see the energy consumption, high, from 183 to 196 kilowatt hours per square meter per annum. And that by August, we reached about 209, which is incredibly high. So then the people started to use the building, and we started to learn how to make the building, how to use the systems in the building. And so by February, we got down to about 173. The average commercial building in Singapore uses about 253 kilowatt hours per square meter per annum. And this building uses, the study here shows 173. And these were the post-occupancy evaluation of the building. I'm not sure these were fudged by the consultant, but it says that the users were 99.7% satisfied with the building, and the staff, obviously they wouldn't get paid enough, got paid 7.5. But here, this is the energy pie, and the Singapore building uses 230 average building, whereas the library actually the air conditioning is never switched off, and so by all means and purposes it's actually a very low energy building, and after construction is around 160 to 170. This is what it looks like from distance. A more recent project is this one. We just started work in July this year. Again in Singapore, we had green roofs, and we had vegetation that spirals up the building. You can see the red line, and then we have the eco-sun on the left-hand side, and then we have an atrium in the middle. An interesting device we use in this project is what we call a solar shaft, where we bring daylight into the inner parts of the floor plate. So biointegration to me then became the answer, and I thought if we're able to biointegrate everything that we make and we do with the natural environment in a seamless and benign way, then we wouldn't have any environmental problems. Obviously, this is easier said than done, But how to make this work has to be the biggest challenge that confronts all of us as architects and designers today. So I thought about it and I said maybe we could structure this biointegration. And so I started to look at it in 3 levels: physically, systemically, and temporally. Now, what do I mean by this? Here's a poor gentleman with various artificial things attached to him, artificial leg and kneecap and so forth. In many ways, what we do as architects is very similar to what doctors and surgeons do with the human body, because a prosthetic device is an artificial thing that we make. It is synthetic, it is artificial, human-made, and has to attach to a host, the host organism. And the success of the prosthetic device totally depends on how we integrate the two together, the artificial component with the natural component. So by analogy, our buildings are like prosthetic devices. Well, not just our buildings, but things we make, like bridges and roads and ports and airports. And they have to integrate with the biosphere. So the equivalent of the host organism, which is the human body, is the biosphere. And everything centers around successful biointegration. And to me, these are the 3 levels: physical, systemic, and temporal. Physical means integrating, for me, with the existing features in the ecology of the environment, because every part of the earth is different. The ecology is different, and that it has natural features, has physical features. The topography is different, the soils are different, hydrology is different, and we have to integrate in a seamless, benign way physically. And then each part of nature has processes within it. I call them ecosystemic, and that's the climatic processes. And so we have to make sure that we integrate with the processes in a seamless and benign sort of way. We shouldn't emit too much excess heat. If we have a power station, the pollution it emits mixes with the air in the environment, and the wastewater gets discharged into the waterways and affects obviously aquatic life. And finally, the 3rd level of integration is temporal. The way we use resources, the way we use non-renewable resources and renewable resources, we have to conserve them temporally so that it allows for the use of future generations. And so physical integration has to do with looking at the ecology of location. So back to this gentleman with an artificial hip. Before you can connect this artificial hip to the hip bone, you have to understand the substrate. So in a similar way, we have to look at the substrate of the ground, of the land, before we put anything upon it. Now, if you ask an ecologist, you cannot study an ecosystem in a day, you cannot study in a week. You have to study diurnally over the seasons of the year, sometimes over several years, before you can understand the energy flows, the biodiversity, the material flows, state of succession, and so forth. But as architects and designers, we don't have the luxury of time. We can't do this. Otherwise, we spend 3 years, for several years, studying the ecology before we put up a building. Nothing will get built. And so, around the late 60s, landscape architects came up with this method, which we call the layer cake method. So you can map a location in terms of geology, hydrology, and so forth. You can see the first diagram. And then as a quick way to understand the ecology. Now this is a shorthand. We should be very careful that we don't see this as the end all, because if you take each of the components in the diagram on the top, you find that the diagram on the left hand side shows that they interact in very complex ways. So we really have to understand not just how they map and how they overlay, but how they interact vertically. In a nutshell, this method is what you call the ecological land use planning method. You map it on the left-hand side, you put a grid over it, you assign points, and you get on the bottom right-hand side a composite map, which provides a guide, if you like, for laying out the development. Here's an example of what this looks like. This from mapping that you do and you overlay. On the bottom right-hand side is the composite map that tells you that you can put development on the buildings and structures and roads on the red parts of the site, with a bit more care on the orange parts, but never on the blue parts of the site. So you can see a diagram on the left-hand side and the development that's laid out on the right-hand side. Here's the sort of image of the project. So I started to develop what I call taxonomy of sites. When I look at a site for the first time, I ask myself whether it's an ecologically mature site, an ecologically immature site, a mixed artificial monoculture, zero culture contaminated site. Ecologically mature sites are a site which is like a pristine ecosystem, like a rainforest, or a pine tree forest, which have not been affected by human beings. Immature would be one which is partially affected, mixed artificial, like a landscape park, which is part human and part natural. Monoculture would be like a cornfield where there's one predominant species, and then zero culture would be an urban site where there's nothing, topsoil's gone, flora and fauna's gone, hydrology significant effect, and so forth. And contaminated would be a brownfield site. Interestingly, the other day I gave this lecture about ecologically mature site, immature, mixed artificial, monoculture, zero culture, contaminated. And somebody in the audience says, it's a good structure for evaluating your friends. But for the first five categories, you have to map it in the way that I presented earlier on. And this is, if you like, a table that tells me how much. The first one classifies the different types of site. The second table tells me the amount of information I need before I start designing. And then the third table is a guide that tells me what I should do, what are my objectives in looking at on that piece of land, on that site, whether I should preserve and conserve and avoid any building as an ecologically mature site, and so forth. So if you like, it's a guide for planning. Temporal has to do with consumption of resources and how we use energy, especially non-renewable energy. And so I can't cover all these items today, but here's an approach to low-energy design. Architecture is about creating conditions of comfort, which is more comfortable on the inside than it is on the outside. If we don't need architecture like this tent, then we would all be on the outside and we'll all be wet with the rain. And so architecture, if you like, begins when we want to have comfort conditions better than what it is on the outside. And so I conclude that there are four basic ways of creating conditions of comfort. I call them passive mode, mixed mode, full mode, productive mode, and composite mode. Passive mode means improve comfort conditions without any mechanical electrical systems. If you look at the native dwellings for any locality, because in those days they didn't have electricity, they didn't have mechanical electrical systems, and so native dwellings were built to improve comfort conditions without any mechanical electrical systems. So if you go to the Cotswolds, and you can see thatched roofs with very thick walls, and you find that those buildings were actually very comfortable both in the summer and winter without the use of any mechanical electrical systems. Mixed mode means some mechanical electrical systems. Full mode means a conventional building where there is full mechanical electrical systems. And productive mode is where you start to generate your own energy through photovoltaics or wind or different sources. And composite mode would be a composite of all of the above. Now, the basic approach to green design or low energy design is to first optimize all the passive mode. That means through shaping of the building, through orientation of the building. Another word for passive mode is a bioclimatic design before you adopt any of the other options, because the building is comfortable to be used without any mechanical electrical systems. Now, can you imagine if you don't adopt this approach? In the case of a brownout, there's no electricity, then you have to leave the building because it's totally uncomfortable to be in. And so it makes sense to adopt that approach. Now, what you have here is a cold winter and a hot summer. You have two various seasons. And that if you see the dotted line, the little dashed dotted line on top, those are the environmental conditions. With passive mode, you can improve the comfort conditions a little bit in winter without the use of any electromechanical systems. For instance, if you have airtight walls and you have thick insulation without the use of any heating, the comfort conditions are better. Mixed mode can improve on passive mode, but full mode is that straight line at the bottom, or in the middle. Now, what this diagram informs us is that passive mode and mixed mode can improve your comfort conditions, but it can never ever compete with full mode. And so what this diagram tells us is that if we insist on comfort conditions consistent throughout the whole year, we are in a high energy situation. So quantitatively, this is what it means. Full mode, we'll be talking between maybe using 230 to maybe 300, 400 kilowatt hours per square meter per annum, an energy index. Mixed mode would be between maybe 60, 70 to 160, and passive mode would be in the 60 and above, below, because you still need energy for lighting and for power and so forth. The Building Research Establishment recommends standard for offices to try and achieve an index of 100 kilowatt hours per square meter per annum. But what this diagram informs us actually is that low energy design, or designing with the minimal use of energy resources, that's a lifestyle issue. It's not a matter of design, it's not just the realm of the architect or the designer or the engineer, but it's us as human beings. Now, if we're prepared to be a little bit cold in winter, wear warmer clothes in winter, then obviously we need to use less energy for heating. And in summer, obviously, if we wear thinner clothes or run around starkers, we probably use less energy. Now, bioclimatic design has to do with shaping and passive systems. For instance, proper shaping of the building and orientating it, proper facade design, good glass to solid ratio, use of solar control devices and sun shading, use of natural lighting, use of wind and natural ventilation, and so forth. These are different ways that we can actually improve the energy performance of the building, and we should optimize all these options before we do anything else. Here's a building that we did about maybe 15 years ago, and we shaped the building and configured it in relation to the sun path. We look at the sun and we said, well, the site is about 2.9 degrees above the equator, and the sun is almost east and west over the whole day. So we put the core, the elevated core, on the hot side of the building on the east side, so that as the sun builds up, during the day, it keeps the sun away from the usable spaces. Now, the diagram on the left shows the tower as it's built. You can see the core on the east side, and then we look at option 2, which is core in the middle, or option 3, which is the core to the north. This is to illustrate that shaping of the building is extremely important at the outset. We took an index which is called OTTV, which stands for Overall Thermal Transmission Value, and for the first one is 43.3 watts per square meter, second is 47.5, and the third is 47.6. Now, as an index, what it means that this diagram informs us that if you start with the right shaping of the building, the right orientation, you start with a low energy building before you put anything else in. Then anything else you put in can only further enhance its energy performance. But if you don't, then you probably have to have additional heating systems and cooling systems, which then makes total nonsense of designing a larger building. And so this is what you call designing with climate, or bioclimatic design. Now, until about early 50s, for most architects who were trained in that period, designing with climate is a second nature to them. But something happened in the 60s. Energy became cheap. Architects became, and engineers thought, well, we don't need to design with climate. We can shape any building that we want, and that we can use cheap energy and the mechanical ecosystems to cool and heat the building. And that has persisted until today. If you go to any school of architecture today, you'd be hard-pressed to find any school of architecture that teaches what they used to teach architects in the 50s, which is to design with climate. So if we were to do anything, if we were to sort of retrain architects, we should teach them bioclimatic design, design with climate. But there again, it'll be another 10, 20 years before they get in a position of Winston where they start doing buildings that matter. Now, sometimes we start with an idea. This is an apartment building that we just finished last year, and the biggest issue for us in the apartment building is how to ventilate the kitchens and the toilets at the back of the apartment. So with this idea, we had a circulation system in the middle, and we had voids to bring ventilation to the back parts of the building. So the idea was to have a wind catcher at the bottom of the tower and wind catcher at the top to catch the wind and then channel it inside the building. This project is in the tropics, so it was fairly easy because we only have one basic season. And so we started to simulate it by CFD, and you can see on the this was done at design stage, that the comfort conditions, as you can see, is on the left-hand side, and it has to be within that light blue and the light yellow. And then on the right-hand side, you can see that channel space in between the two sides of the building. And you can see the colors are more or less acceptable. These are different simulations. And then we start to look at sun shading for the building, and then we look at what happens if what you see on the left-hand side diagram is without sun shading, the heat enters the building, and it makes it incredibly hot with hot air condition. And the right-hand side shows what happens when there's sun shading. And this is the graph from 12 o'clock in the morning, or 0 hours in the morning, to 12 o'clock at night. And you can see the hottest time of the day is around 5 o'clock to 6 o'clock. And the blue graph shows that without sun shading, it gets incredibly hot. It shoots all the way up around 4 to 5. But with the sun shading, you can see the red graph. So this shows the sun shading actually works as a passive device to reduce the need to cool the building. Right now, we're looking into food production and the green design also as a new production. And I call this BIFP, which is Building Integrated Food Production. This is a tower that we've done for one of the richest people in Malaysia, and he is into food production. And so he said, I wanted a green facade. And he said, well, make it productive. So we put the food growing device in the two sides of the building. And this is what it would look like on the inside where you could grow food in the building. Now, I'm going to end in a minute, and I'm going to ask you if you could bear with me if I can talk a little bit about theory. If you look at our human environment, this actually has a whole series of very complex processing activities. We take materials, agricultural products and fossil fuels on the left-hand side, we process it and we use it, and then we throw it out in the environment. What you have is a throughput. If we can simplify this, then what you have is something like this. And that when we talk about the life cycle of a building, it is the first environmental impact, which is the energy, environmental consequences of creating that building. And then second is the operational stage in its life, which is when it's in use. We also have to be concerned about what happens at the end of its useful life. Most architects do not concern themselves with the operational impact, and if they do, a lot of them don't care about the building, what happens at its useful life. But you have to. This is what ecological design is. You have to look at the life cycle of the building from the first impact to the end of its useful life. Of course, the built system is not just about architecture. It's about everything we make as human beings. Whether it's bridges, roads, toys, refrigerators, or clothes. We have to see what happens to them. First impact, what are the consequences of the environment, and then when they're in use, and what happens when a piece of clothing is no longer used. Do we just throw it away, or we buy back, or what do we do? Now, if you look at it in entirety, then at each of these stages, for instance, the first environmental impact uses energy, uses material, and then as people getting to that building and leaving it. And then you have opposite of energy, material, and then the built system, what happens to it at its useful life? So you have inputs and outputs. That each of these stages, the use of energy, use of materials, have impact on the local ecological systems, has impact on the biosphere and its climatic processes, has impact on the global energy material resources, and has impact on other existing environments. So green design is much more complex than people think it is. In fact, you should think about all these at the same time, acting together as a whole. And obviously you can see on the right hand side, the output should try and be returned back into the building for reuse and recycling. I haven't got time to talk about biomimesis, which is imitating ecological systems, or ecomimesis, because nature existed in a state of stasis before us human beings started to significantly disrupt it. And then we try and imitate processes in nature. For instance, in ecosystems, its only source of energy is from the sun, whereas our source of energy is from fossil fuels and from other sources. So if you look at the ecosystem, everything's recycled. There's no waste in nature. The waste from one organism becomes the food for another. And so everything's recycled and reused. So we should try to imitate this. We should try and reuse materials as much as we can within the built environment. And if we cannot reuse it anymore, we should try and recycle. And anything else we cannot recycle and reuse anymore, we should try and reintegrate back in the environment. So reuse, recycling, reintegration should be what we do with materials that we use in the environment. Now, I could end here, I could talk a little bit more, and so another few minutes before I catch my train. So this is what mathematicians call a partition matrix. And so if you look at everything that happens inside the building as L11, and everything that happens outside the building is L22, and if you look at the inputs from the outside inside is L12, and the outputs L21, then LP is what Ecodesign is about, which is the simultaneous consideration of these four sets of interactions. Because you cannot change one without changing the other. So if you look at L21, which is the totality of independencies from the outside to inside the building, and L22 is what everything that happens on the outside of the building, then let's say in 10 years' time, we run out of fossil fuels, which is very likely to happen. Now, if we run out of fossil fuels, then it affects the inputs, which is L21, which affects what happens in our built environment, in L11, affects our outputs. So, green design really it consists of monitoring all these four components at the same time. And that's why we still haven't got a truly green building today. We're attempting to design green buildings. A lot of architects are working towards it, which is a good thing. But I think we're a long way to go before we're a truly green building.